Good afternoon and welcome to day 2 of this course on compact binary object mergers, rates, and population studies. So today, unlike yesterday, we'll have 2 lectures. So right now we are convened to have the first lecture start. So I think we have a quorum here, both offline and online. So Christopher, it's up to you. Please take it away.
Let me share my screen and hopefully, well, run things similarly to how we did things yesterday, where if you have any questions, please put your hand up or ask in the chat, and we'll try and address those as we go through. I'm just trying to make sure I get the chat up so I can see it. Yes, there we go. Okay, so yes, this is lecture 2, where we're going to continue talking about the astrophysics of compact binary formation. So last time we had a bit of a discussion about why we like the compact binary coalescences, CBCs within LIGO, Virgo, Kagro lingo. We like these because they're a great signal, they're loud so we can detect them far away, and we have definite predictions for what the signal should look like. Here we have a numerical relativity simulation showing gravitational wave signal. Oh, that's showing the in-spiral. And because we know how the properties of the source impact the signal, we can work backwards from the observed signal to the inferred properties of the source, which is all very nice. So just as a little example of this, let's skip ahead. Next slide. Here are the gravitational waves from our first observing run of advanced LIGO back in 2015, 2016. In this panel here, we have the frequency, the time evolution of the signal, so similar to what we saw in the last panel of 1509-14, our first detection, what was originally called LVT 151012, now renamed GW 151012, and GW 1512-26. And you can see these signals are quite different in their shapes. That 1512-26 has a much longer in-spiral, is much quieter overall. And then if we, the color indicates which signal it is. In the first animated video, the color represents the curvature of the space-time underneath. Okay, so coming back to here, here we have our 3 signals in the time domain. You can see various lengths. And if we transform this to the frequency domain, so if we do a Fourier transform of these signals, you can see that these correspond to different frequency ranges. So 1509-14, here's the loudest signal. We can tell that from the amplitude of the signal here. Also merges at the lowest frequencies. It's the shortest signal. And this corresponds to the highest masses. So high masses, big black holes, they merge where they're still quite far apart. That's a low orbital frequency. That's a lower gravitational wave frequency. Whereas 1512-26 keeps merging up to for much longer, up to higher frequencies. So that corresponds to a lower mass signal. 1510-12, somewhere in between. And from knowing the masses of the source and how loud the signal is, we can infer how far away the source is because the amplitude of the signal decays away. So we like compact binary coalescences because they're a loud signal. We know what to look for. We know we can learn important things about their sources from them. However, we discussed last time that we have a concern with seeing an astrophysical population of these sources because they take so long to in-spiral, that they need to start really close in order for them to merge due to gravitational wave emission in a reasonable time. So we need some way of starting the black holes, or black hole, neutron star, neutron star, neutron star, close together so that they can merge due to gravitational waves. Now this is difficult because the type of distances we're talking about are smaller than the size of the stars from which these black holes or neutron stars would have formed. So if they were that close together when stars, they would have merged together and to form one big star as opposed to having two stars, which is no good for producing a detectable source of this. Okay, right. So I've got a message that my video is freezed. Can you still hear me okay?
I can hear you.
Okay, so it doesn't really matter if you can't see me as long as you can still see my slide. So can you see, this should be the orbital evolution slide.
Yeah, and we can also see your pointer. So
cool. Okay, so minor hiccup, but yeah, please let me know if anything does freeze up. Okay, yes, we want mechanisms to get these black holes or neutron stars close together. And we started speaking about the different channels last time. So now let's go and start talking about these again. So we talked first about dynamical formation channels. So the idea here is to avoid the problem of having two stars very close together, as my cartoon representing two stars splooshing together, we can just try and get black holes close together. So the idea here is that we have a dense environment where there are many, many objects in a small space. And then as these move around, every so often a couple will get close enough to form a bound pair. We form a binary that way, or I guess initially we could also have binaries that did leave all their lives together as stars, but started out sufficiently far apart that the stars didn't merge. These were very far apart, but due to all the interactions of objects flying by, those tend to harden binaries, so make them tighter, so shrink the orbital radius. Oh, can I explain this? Okay. So these dynamical interactions will shrink your orbital size so you can get within the gravitational wave emission regime. We can also potentially have say, a binary with a third object around it in a three-body system, and that can also drive the orbit to shrink. So the types of environments that this would happen in maybe a globular cluster, nuclear star cluster often talk about, so very dense environments where there are lots of things in the same space. Related to this, we spoke about that how nuclear star clusters in the centers of galaxies. Centers of galaxies have a supermassive black hole and this core of stars around it. We can also have a disk of material, an accretion disk around the supermassive black hole. This is what powers an active galactic nuclei, and we get jets of things being blasted out. But we can also have things embedded in this disk, and we can have the viscous forces drawing things together and accreting onto objects to make black holes even larger. So we have this way as well of making binaries. Now we were starting to talk about, okay, what if we do have two stars in a binary together? Can we think of some ways where we can get these to form a pair of black holes that are close enough together without the two stars merging together in the first place? So we ended the last lecture talking about chemically homogeneous evolution. So the idea here is that if we have two stars close together, need to be in quite a sweet spot in terms of the separation, then they can their self-gravity raises tides on the two stars that causes and as these rotate, these are tidally locked, so these stars rotate. Why this rotation is important is that normally in stellar evolution, what you have going on is you have a core where you're undergoing nuclear fusion, that's forming heavier elements in an envelope which remains lighter elements. And over time, the core develops, and eventually the outer layers puff up as the evolution progresses, and this is what leads the stars to expand. In chemically homogeneous evolution, because you're mixing all the layers together because of this rapid rotation, you don't have the same growth of the core, and so the envelope doesn't come into this as well. So this prevents the stars expanding, which means that they can live their lives quite happily without merging together, and you end up growing quite large black holes because you have a sort of a larger equivalent of the core in the middle. Okay, does the concept of mixing length come into the picture when rotation induces chemically homogeneous evolution due to mixing? Complicated question here from the chat. So yeah, mixing length, I'm assuming the question relates to a classic mixing length theory, which is how we often describe the way stars undergo convection, and how we have one sort of parcel of star fluid, so that the plasma that makes it up rising up, and how that disperses into the medium. And yeah, I think you can understand a sort of similar thing here, that we have we have very good mixing in these stars, so it becomes homogeneous. So you can try and formalize it in a similar way. I think I'm not expert enough on the specifics of the dynamics of the fluids there to get that, but yeah, I think you can understand it as a way that you have very efficient mixing going on, so you have all the different layers smearing into each other. Okay, so this is one way of getting stars. We prevent them from expanding so that they can live their lives close enough together. However, this is not the main way that we think that you can get isolated evolution forming these binaries. And what we think sort of more happens here is that we start with two stars that are quite far apart. Okay, have one star and another star. They're living their lives quite happily on the main sequence, fusing hydrogen to helium in their cores and so on. Now, the more massive star, I'm drawing this bigger one to represent the more massive one, will evolve quicker. As it starts to evolve, we start getting the outer layers expanding. And so we can get this star getting bigger compared to its companion. Now, as we expand, we can have that points on the outer side of the envelope now get gravitationally attracted to the companion more than their original host star. So we can get mass transfer. We get material being pulled off the star and falling onto its companion. Now, you might see this described in terms of looking at the potentials, and we have a point called the Roche lobe, which does describe sort of the equipotential surface, at which if a star expands beyond its Roche lobe, then it will start getting stripped onto its companion. So if the star expands to the point of its Roche lobe, it starts undergoing mass transfer. Okay, and in the examples, you should hopefully have a bit of a look at this a calculation of the size of the Roche lobe and when the star expands. Now, when we have mass transfer, things in the system change. So as well as this star becoming less massive and this star becoming more massive, there are a whole host of other things that could happen. So we have angular momentum transfer, for one thing. So angular momentum of the material gets transported. So the material here has a certain amount of angular momentum set by the orbit, and that will be transferred here. So if we're just considering of simple taking a blob that of mass, delta m from here to here, that will take some angular momentum to this companion, and that will change the orbit. And again, you should have a look at this in the examples, and that can either shrink or expand the orbit based on the mass ratio of these two objects. Okay, but so that's sort of first order what's going on. But we also need to consider the reaction of the star and the Roche lobe to changing the mass. So when you move mass from this star to this star, you're changing their gravitational potentials. So the Roche lobe is going to change. Okay. Generally, what's going to happen is you're going to shrink the Roche lobe so that the radius of the star that it needs to be before it overflows its Roche lobe gets smaller. So you want the star to shrink as well in order to stay within the Roche lobe, which is not always what happens. So if what happens is we take some mass off, the star shrinks, Roche lobe shrinks, but the star shrinks smaller than the Roche lobe, then the mass transfer will stop. That would be called stable mass transfer. The star would continue to evolve. It might then start to expand a bit more. As it burns more nuclear fuel, it might overflow a bit more. Star will shrink, Roche lobe will shrink, it will limit itself off again. And so we get this gradual transition of mass over a time-scale that's given by the lifetime of the star, the nuclear burning lifetime, which is maybe tens of millions of years or even longer for the massive, for less massive stars. However, if we have something different, if we have it that the star doesn't shrink faster than the Roche lobe, then the Roche lobe will shrink faster and faster. We can get unstable mass transfer, that as we reduce the mass of the star, we just get a higher and higher rate of mass transfer. And this is called unstable mass transfer, as you might guess, and it's a runaway process. Okay, and in this case, we get lots of material being dumped onto the companion. This can happen on 2 time scales as well, because of how the star responds to losing mass. So it can, as it loses mass, it first needs to adjust on a dynamical timescale set by re-establishing hydrostatic equilibrium, so balancing the pressure and gravity of its own star. If it expands beyond the Roche lobe on that timescale, the mass transfer proceeds very quickly. So maybe 10 to 100 years or something like that is all it takes to readjust, and you get this mass transfer there. If after establishing hydrostatic equilibrium, it also needs to relax to become in thermal equilibrium. So to get heat transported takes a bit longer than to re-establish the pressure. And we can also have some expansion as it re-establishes thermal equilibrium. And in that case, we can again have the same thing happen, and we'll get some mass transfer on a slightly longer timescale, something like a Kelvin Helmholtz timescale of 10 to the 5 to 10 to the 6 years or something. Now, important, the type of response you get depends on the type of stars. Generally, if you have a star with a convective envelope, so stars may either be convective or radiative in terms of the dominant way of transferring energy. If they are convective, they will generally expand on mass loss. So whenever you have a convective star at the outer layer, you expect unstable mass transfer. Okay, so gone through the idea that stars will expand. When they reach the Roche lobe, they will then proceed to have mass transfer, and this mass transfer can either be stable or unstable in terms of how much mass goes through. If it's stable, it will be self-regulating, and we get a steady stream of material. If it's unstable, we're going to get a whole host of material getting transferred. So that's what happens on this side. Now let's think about what happens on this side. So the star, this star here, can only accept a certain amount of mass. There's only so much mass that can be accreted onto a star, and it can absorb it. So we can either have conservative or non-conservative mass transfer. Conservative means it gets all absorbed, and non-conservative means that some of it then gets ejected from the system, that we can't have all of being absorbed, so some of it just gets lost to space. And this non-conservative mass transfer is particularly important because we can have the mass being lost carrying away angular momentum from the binary. So angular momentum gets lost from the binary, that will drive the orbit to shrink, and that's the type of thing we want to happen in order to shrink our envelope, our binary, to get closer together. But we don't want it to happen yet. So at the moment, we still have 2 stars. So if we have these being driven together, they're just merged together to form one big star, which we don't want. So we want them to survive this stage. Ideally, we'd have, say, some stable mass transfer. This star will live its life, and then it will explode as a supernova, which we learned about in the seminar last week. So we're going to have an explosion and a collapse down to, say, a black hole or a neutron star, where this other companion now still living its life. So just to stress that there are a lot of things that can happen here. Here we want the right amount of mass transfer so that we don't merge in together. Here we have a supernova explosion. Potentially there will be a kick assigned to the black hole at birth as it loses lots of material. We don't want this kick to be too big, otherwise that will unbound the binary, and we don't want that. We want to still have a binary. So we don't want too much mass transfer. We don't want too much of a kick in order to go through this. So we want to have still a black hole and a stellar companion left after the supernova explosion. What happens next? Well, this lighter companion will continue evolving, and so it will start to evolve and expand. And what we can now have is potentially a second period of mass transfer, as this starts now to overflow its rush lobe, and we get mass transfer onto the black hole. And as again, this can happen either unstably or stably. It can be conservative or non-conservative, depending on what goes on here. So if we have stable mass transfer, non-conservative, this is really good. We can get a nice swirling of material onto the black hole, forming a nice disk, as would be in an X-ray binary. So we know these systems do evolve and form because we see these in X-ray binary systems. The black hole can only accept a certain amount of mass. Some of it will be lost. That will carry away angular momentum. So this will then shrink the orbit. And then when we get the second supernova explosion, okay, we should be left with two black holes closer together than their stars started out. So this distance here is much bigger than this distance here. So potentially they can go on to merge due to gravitational wave emission. Okay, and of course we do have to worry about the supernova kick, whether that might unbound the binary as well. But at this point, the orbit should be tighter. We should be closer together than for this supernova explosion. So the orbital speeds will be much higher. So you need a much bigger supernova kick to unbind you at this point than you would at this point. So if you've already survived this supernova kick, you're very likely to survive this supernova kick. So that's less significant. Okay, so this is isolated evolution first via stable mass transfer. Have a nice disk of material forming on. What happens now if we have the unstable mass transfer? So we have two stars forming. Again, we have our first period of mass transfer. Let's say that this is stable. Okay, we have collapsing down to a supernova. So collapsing down to a black hole in a supernova. Have our second period of mass transfer. But now it's unstable. So we have much more material being accreted onto our black hole, more than the black hole can absorb. And we have a runaway process. The more mass this star transfers, the more it wants to transfer. What we believe happens in this case is we form a common envelope. So the idea is we have our core of our star left, okay, but the envelope has basically all spilled over to the black hole, and we get a common envelope forming around both the black hole and the core of the star. Okay, and then we get these two orbiting around inside this envelope, and we have a viscous drag as these orbit around inside the envelope, and this causes them to inspiral inwards. So it's like moving through a fluid. You get a drag that extracts energy from the orbit that forms you tighter together. And somehow, the details of which are not entirely known, the idea is that you transfer energy from the orbit or other systems to the envelope. That's enough to eject the envelope. So you're left with just the core and the black hole, much closer together now. So then these will collapse down to a black hole again in a very tight orbit, and it can go on to merge. So we bring things much closer together, not through the same angular momentum loss in stable mass transfer, but through ejecting the envelope and having the viscous drag into the common envelope. Okay, so we know common envelopes should be a thing. We see systems, lighter mass systems, say, that are the results of this, but we don't understand exactly all of the physics that goes into this. This brings us closer together. That's what we got to merge. And if you look in the literature, it's often this channel which is commonly described as the main way of getting isolated binaries to form. This was sort of the first channel that was suggested for forming the type of observations that we see. Okay, so how are we doing in terms of making sense? Does anyone have any questions on these isolated evolution mass transfer channels?
Is that an argument to say whether the more massive progenitor will necessarily be the more massive black hole?
Fantastic question. Yes. So let's go through this. We said that the more massive star will be the one that evolves faster. And typically you'd expect the more massive star to have the more massive core. So when it collapses down, it will form the more massive black hole. However, we note that we have mass transfer going on. Right? We have mass from this star going to this star. And if we transfer enough mass, we can make this star the more massive. So potentially we can get a mass ratio inversion is what it's called. And so the second born star can end up, so the initially lighter star can end up producing the heavier black hole if we have enough mass transfer. This normally needs to happen by an extended period of stable mass transfer early on. You need the stars to start off quite close in mass in order for this to happen. But yes, that can happen and can have some interesting circumstances. We do also have some mass transfer back later on, which you might think can correct it, but it very much depends on how much mass can be accreted. In particular, in the common envelope prescription, the envelope is quite diffuse. So when you have the black hole moving through it, there's very little mass that it accretes, and the common envelope phase is very short-lived on astronomical timescales. Potentially, it's not that many orbits in order to expel the envelope. So very little mass would be accreted at this point. If we have stable mass transfer, we can accrete more. However, because this is a massive star, it only lives for a few million years or something in this phase, and that's not a significant amount of time for a black hole to accrete lots of mass. Yeah, it can be difficult to grow your black hole here. So yeah, you can have an inversion. It's typically dominated by whatever happens at this point in the evolution.
Thanks.
Okay, any more questions?
Hello.
We're going to come back to talk about a few things in detail. So
hello, I have a query.
Yes, please.
Yes, so when these two stars are conventional stars and there is a mass transfer from the one star to another, why there is not formation of accretion disk like we have in the star is a compact object?
Mm-hmm. Yes, that's a good question. So potentially you can have some kind of disk of material depending on the geometry. The real difference between here and here is the physical size, that stars are quite big, whereas black holes are very small. To actually get accreted onto the black hole, like, you need to get all the way down to the, something like the last stable orbit, which is a few gravitational radii, which means you need to lose a large amount of your angular momentum, right? Because you're going to start off, you have one star and another object here. You're going to have material come out and it's going to swirl around, right? Because this is in a rotating frame. Coriolis forces, if you got things coming in, and you're going to need to spiral in to come down. Now, the amount of spiraling you need to do in order to get to the middle depends on the size of the object. If you're just hitting a star, you don't need to lose too much angular momentum to get all the way down to the surface of the star. If you need to get all the way down to the black hole, you need to lose a huge amount of angular momentum. So you need to form a disk, and you need to, in order to have the viscous forces that will cause the losses that will allow you to spiral all the way in. Okay, so I hope that sort of makes sense of why the disk properties can be quite difficult. You can still get something disky-like in this case, but it's not the really sort of X-ray bright type disks where you have all sorts of interesting physics going on here. How does the Roche-Low, question, how does the Roche lobe change with mass transfer? Is it proportional to the mass transfer rate? So good question. I think two things here. The Roche lobe, you can parameterize this basically just in terms of the mass ratio of the two stars. So the rate of change of the Roche lobe will depend on the mass transfer rate, but the position of the Roche lobe at a given point doesn't depend on the mass transfer rate, if that makes sense. So the change of the Roche lobe radius with time depends on the mass transfer rate, but at any given moment, the position of the Roche lobe just depends on the size of the two stars, the mass and their orbital separation and mass ratio. Question, can the common envelope evolution happen without or prior to the formation of the black hole? Yeah, potentially we could have a double common envelope evolution if we have unstable mass transfer at this point. This is much more difficult to survive, as in this case, you can have things spiraling, this star spiraling in, and because these are much more massive stars, it's much easier for them to smash together at these points and just form one big star. So it's much harder to have a double common envelope evolution that doesn't result in the stars merging. But there are predictions for that to happen. So yes, good question. I was hoping someone would ask that.
Hello. I have a question. We started with two different mass stars. So what would happen if they're equal mass? Would we expect like two Roche lobes?
Yeah. So yeah. So I guess there are two questions here. So if it's going to be impossible practically to have stars which are exactly equal mass. Just the fine tuning is going to be very difficult. If they're really nearly equal mass, then yes, they can start expanding at very similar times. And so the mass transfer physics will be somewhat more complicated, as you have to deal with envelopes forming at the same time and mass going. So I guess yeah, you're much more likely, I think, to have them both puffing up and forming, having more complicated mass transfer. The typical timescales for evolution are normally much longer than for the mass transfer phases. I think what might happen is you're more likely to cut stable mass transfer short as one star expands, and that will cut things off, and you'll start messing around with the envelope at this point and having perhaps common envelope forming instead. Or you have them merging together and no longer forming a binary if they're really close in mass. So exactly what happens will depend on many things like the orbital separation. If they are very close in mass, yes, you can get more complicated physics going on. That's often not modeled particularly well in some of the approximations used, because you like to assume one star or the other. In practice, it's often quite hard to have them close enough in mass that they evolve at exactly comparable times, because the difference in timescales associated with mass transfer versus nuclear burning in the center, which sets the evolution timescale.
Thank you.
Potentially a good project to look at is try setting some stars which are close enough in mass that they almost evolve at the same timescale, but don't evolve perfectly at the same timescale.
Hi, so I also had a question. Can these systems also form circumbinary disks, as there are models for supermassive black holes?
So a good question here. So yes, I think is the answer here. Can we get a circumbinary disk? So there are a couple of ways we can get a circumbinary disk. Basically, we just need some period where we're losing mass from the binary, but it doesn't quite get unbound. Now, if we want circumbinary disk, we probably want some material that sticks around right at the end and two black holes. So there are, I guess, 4 points at which we're having material ejected from the stars, one of which I've not mentioned yet, but is important. So let's start with that one. So first up, stars throughout their lives lose mass. There's a stellar wind, material streams from their surface. In our solar system, we know there's a solar wind. This is what gives us the aurora, so that's quite nice. Massive stars have stronger winds. The winds are often driven by the luminosity of the star. So the more luminous the star, the stronger the winds are. The more massive the star, the more luminous it is, and hence we get masses. So we're going to have stellar winds carrying away some mass. Some of that perhaps might not get completely through the system and might sort of float around in a diffuse envelope. There probably isn't going to be too much of that just due to the amount of material lost in winds is not that high. But that's source one for some material around the binary. We then have the supernova, the first supernova, that will blast off some material. Potentially, most of that will, say, get unbound, but maybe some of it falls back. In black holes, we believe a lot of it, the material ends up coming and collapsing onto the black hole, but some of it might not quite make it away and might form a binary around it here. Then we have the second, we have material from mass transfer. So either non-conservative stable mass transfer, we get some material being lost, but it might not be completely lost. It could be orbiting around still. Or from the common envelope ejection, as the envelope gets ejected, all of it might not make it very far away, so some of it may remain. Okay, all of this material potentially could then get cleared away by the second supernova explosion. So this will blast off, maybe that will strip off remaining gas, that's maybe, or maybe some of it remains. But again, we do have the second supernova where some material is being ejected. Not all of that will maybe escape. So it might be that we end up with two black holes with a little bit of gas all around it, and yet that could maybe start to collapse down to a disk over a suitable timescale. And potentially why you are asking about this, as this has been hypothesized as maybe a way of getting an electromagnetic counterpart to a binary black hole merger. That when you get the black holes actually merging, they'll form a single black hole. And because the gravitational waves carry away energy and angular momentum, well, mostly energy actually in this case, the black hole left is going to be less massive than the sum of the two black holes. So if you had material in a nice stable disk around the binary, it suddenly finds itself in orbit around something which is less massive, so it's no longer on a nice stable orbit, and so you're going to have the orbit destabilize, and some of that material then potentially will spiral inwards and accrete onto the black hole, and so you might get some electromagnetic emission at that point. And that's been hypothesized as maybe one way of having an electromagnetic counterpart to a binary black hole merger. The amount of material generally left behind isn't that large, so it's maybe not going to be the brightest of counterparts, but it has been suggested. Cool. Okay. Any more questions now? Okay, so I think there's just a couple more things now to talk about in terms of evolution. So first up, if we go back, we've now talked about three different ways of having a binary together in isolated evolution to form a binary. So chemically homogeneous evolution, the most, let's see, perhaps the most special case, we have stable mass transfer and unstable mass transfer common envelope evolution, which can both lead to formation. Those are sort of the classic channels suggested, particularly the common envelope. We've spoken about the dynamical channels, where we don't worry about forming the binary together, but we just assemble the binary later on. So now is where we come to the point where people will often say things about, it'd be really nice to tell apart dynamical and isolated evolution. However, a thing to bear in mind is there's actually no such thing as isolated evolution. Most stars, although they might be in a binary when they're formed, they will be formed in some open cluster of stars. So there are many other stars in the local neighborhood. Over time, because this is an unbound cluster, these stars will drift apart. Okay, and so we don't need to worry about them interacting. We don't, worry about other stars close to our sun, for example, because they have all drifted away. But early on in the evolution, potentially there are many stars in the area, and so we can get dynamical interactions potentially even for stars which we would think of as being born in isolation. And this is particularly important because the most massive stars have the shortest lives, So the ones that form black holes will evolve over the same sort of timescales where these interactions could still potentially be reported. So dynamical interactions in young clusters are potentially important too. We don't have the same density, and so we don't have the same number of interactions as we do in globular clusters, but potentially there's still dynamical interactions going on, which does complicate the picture of understanding, just isolated versus dynamical. So whenever you're reading about, either this channel or that channel, remember that's a simplification. There are other things going on. And we can even have things like we can have a three-body system forming for a star in what would be a binary in a three-body system, third companion. And so the influence of this body can also impact the orbit, can drive this closer. So we can get extra complications here. So I think, as always in physics, we start off with simple models and we add more and more complications to it as we get a deeper and deeper understanding. So most of the time we'll just talk about dynamical formation versus isolated formation, but we need to remember there is some overlap in the physics of the two channels that does complicate the complete understanding of what's going on. Okay, now that covers all the ways of forming black holes from stars. There's one more hypothesized way of forming binary black holes, which is via primordial. Primordial black holes. So the idea here is that for astrophysical black holes, which is how they are called in the literature most commonly, we start with a star, it evolves, we'll get the supernova explosion, and a black hole left at the end. The size of it will be really set by the core of this star. Okay, so we have black holes forming from stars. For primordial black holes, the idea is that earlier in the universe, we had our universe made up of just a bunch of material, not clustered into stars and things yet, but with various density perturbations. We know the universe had fluctuations in density. That's what seeded the large scale structure, seeded the formation of galaxies and everything else we have going on. So we have a whole bunch of density fluctuations. So I guess if we have some density as a function of position, we're going to have some distribution of what the density is like. And but this is a random process, perhaps seeded by quantum fluctuations early in the universe or anything else of these early universe processes. But if our density fluctuation is sufficiently high, potentially we can get it to a point where we have some criticality and the material will collapse down straight into a black hole. So we have material collapsing straight from just the general gases making up the universe, or plasmas, I guess, perhaps at this point in the universe, collapsing straight down to black holes. So we skip entirely the whole forming star point of this. So potentially throughout our universe, at random points, there will be primordial black holes that just formed, seeded very early in the universe from density fluctuations. And if a couple of these happen to get close enough together, it's exactly the same sort of processes as we were talking about in terms of globular clusters or nuclear star clusters, that we have things moving around, getting close to one another, and potentially forming a binary and going on to merge from that. So primordial black holes are another example of dynamical formation. The difference being they're not formed from stars, they're not formed from a star cluster, but they are formed from primordial black holes. These black holes formed from density perturbations in the early universe. Okay, so lots of options for forming binary black holes. We have different astrophysical black hole formation channels. We have primordial black holes potentially in the mix as well. We don't know if these definitely exist, but there are theories that say that they do. So we would like to try and untangle this physics and see what's going on. So to do this, we would really like to understand the different properties of these various formation channels. So we need to know a little something about the properties of black holes. So we did talk about this a little bit early on, but now let's come back and talk about this again down here. As you know, let's skip over yeah, let's actually take a moment to talk about this before I show you the results. So let's go back. Okay, so what properties are we interested in looking at to identify our channels? We have a mass 1 of the heavier black hole, have a mass 2 of the secondary black hole. We have spins. We have redshift. So this is some.
Hello.
Hi.
Hi, I had a question about the primordial black holes idea that you put forward.
Mm-hmm.
So, how do we even, I don't understand why we're even considering primordial black holes as an option, because their masses are way too small. And even if we considered them to increase their mass by consuming matter around them, how will the timescale of the universe account for the sizes of black holes that we see today?
That's a good question. So the question really, though, is what is the mass spectrum assumed for primordial black holes? So typically, this is set by the formation process, and it depends on various assumptions about early universe processes. So in the literature, you'll quite often see, that's a good question, this will actually connect to what we're just about to go on to, some kind of assumption of a mass spectrum, okay? So number of black holes as a function of mass, and it will have a characteristic scale associated with it. Often assumed to be sort of a log normal distribution or something like that. There are arguments that this is maybe an oversimplification, but this is commonly used in the literature. So let's use it for our discussion that's going forward. The characteristic scale depends on the properties of the universe when you have the fluctuations going on. So density here at this epoch and the spectrum of fluctuations and so on. And this can be of order of a few stellar mass for various, I think QCD in particular, transitions in seeded transitions in the early universe. So the exact point you put this is largely unknown. You can invent theories that will move this around, but this can potentially be of the right order of magnitude for, say, 30 solar mass black holes. So it is possible in some theories to get black holes of the right scale. And as you said, there is also potential for these black holes to grow over time. So even if they form small, they spend much of their time being surrounded by gaseous material. This, of course, can spiral in and accrete and grow the black hole over these timescales to make it more massive. So there are predictions that there will be black holes in the right mass range for our observations we see. We do have the issue, though, of we do also need to get them close enough together to merge. And so the distribution of black holes and the clustering of them is one of the key uncertainties in order to predict the rates of these systems. So good question. There are theories that say you can do this. Whether or not you believe those theories, though, is a slightly different question. Okay, so yeah, this is a good question that does connect back to just what we're saying. What can we observe about our black holes? So we have their masses, we have their spins, have their redshift, so where they merge, and potentially we also have eccentricity, which we spoke about last time, which is hard to measure, but is potentially still there. With the spins, we potentially have both the magnitude of the spins and the orientation. So how big the spin is and the relative orientation changes between the different channels. So these are the different things that we can hope to measure. and these are potentially different for the different channels. So if we go through them, and let's start off then with our primordial black holes. Okay, primordial black holes, we have uncertain masses for what they expect. This depends on the theory. Okay, so this is, depends on your theory. But we can potentially grow from accretion as well. So this is primordial black hole. So we're lacking potentially a good prediction for what these could be, but we know we can get a whole host of different answers. For the spins, the magnitude is typically predicted to be very small. Okay. The density fluctuations typically don't have a lot of angular momentum associated with them. So when they collapse down, we expect a small black hole spin. So maybe 0.01 spins characteristically have a Kerr described by a Kerr parameter that goes between 0, which means non-spinning, and 1, which is maximum spinning. So primordial black holes are typically small, but they can maybe be spun up by lots of accretion. So they can be small plus some growth from accretion. And so that will depend on exactly how long they've been around. For the orientation of the spins, well, we're forming these dynamically, right? There's no preferred orientation. We're just throwing things together. So there should be an isotropic distribution of spins. Okay, isotropic distribution of spins. Eccentricity is not clearly defined, but because that's dynamical, there can be some potentially, depending on the orbits they form from. The redshift here is perhaps a key point. Because these are formed very early in the universe, we're going to get a whole range of redshifts involved, but potentially can be very early as well. So potentially, if you have a detector that can see very far away, and if you can see mergers at a redshift of, say, 20 or higher before the first stars are forming, then you must have a primordial black hole, because those are the only black holes that could have formed. So we have early and then not much evolution, because we're not forming new primordial black holes. We just have the same black holes inspiring together. We have no new generation of black holes. So primordial black holes, not too sure what the masses are. We think the spin should be small and isotopically distributed. Redshift, we know they would be around very early in the universe. Unfortunately, we can't detect that with current ground-based detectors. Shouldn't be too much evolution in the rate. Might be some eccentricity is dynamically formed. Now, if we come to our isolated evolution channels, okay, what do we have going on in these? Well, we know that our masses are basically going to be set by the masses of stars. So we get this from stellar theory. We'll come back to look at this in a second. Okay. We know that we're going to have some, it's not just going to be the same masses as predicted from stars in isolated evolution, because we have mass transfer that will change things. So, and we spoke about potential of having a mass ratio inversion. So there is some complications here. Yeah, so there's going to be maybe not exactly the same as from isolated stars, but the first order it's set by the properties of stellar evolution. We're not going to get much accretion during the common envelope, but maybe during stable mass transfer we get a little bit, because this is a short-lived phase. It's probably not enough to grow the masses very much. Now, what about the spins of our black holes? Now, this is a currently open question exactly of what the spin of our black hole should be. And this really depends on how tightly coupled the envelope of a star is to its core. So we know that the core is going to collapse down to be the black hole. And hopefully you're familiar with the idea that if you have something very big, collapse it down to something very small, it's really quite easy to spin it up very fast. Things that are big can be rotating quite slowly, but because of the way angular momentum scales with radius, you collapse that down, that can spin things up quite high. So in a star, it doesn't need to be rotating very fast to lead, to a collapse down to a black hole which have maximally rotating spin. However, we also have processes that carry away angular momentum. So stellar winds, we're taking material and moving it to a far distance. That's going to carry away angular momentum and so slows things down. We're also going to have the outer layers being lost, supernova explosion as well, carry away angular momentum, and it's really only the core left at the end. So it depends on how coupled our envelope and our core are. If we can couple things strongly, we can potentially get all the angular momentum removed and end up with a very slow rotating black hole. So if we have efficient angular momentum transfer, we end up with slowly spinning black holes. If we have things decoupling, then we can have all the angular momentum in the core going down into the black hole at the end. We don't know exactly how angular momentum transport in stars works, so exactly how the core of the star is coupled to its envelope. So this is something that's currently uncertain. But many of the models predict that we should end up by default with a black hole that's slowly spinning when it collapses down due to angular momentum transfer. So angular momentum is lost from the core to the envelope as the envelope expands out. That slows down the rotation. The envelope then gets blasted off, and so the core is left with very little angular momentum, so it collapses down to a black hole, very little rotation. If the envelope could expand out with, well, the core step didn't transfer angular momentum, so the core would be still quite happily rotating, things would be slightly different. Okay, so we're predicting that black holes often should form with little angular momentum. However, there is some potential to be spun up if we have stable mass transfer here. So if we have an accretion disk, that's going to transfer angular momentum. However, because this is a short evolved phase, we're not going to have enough accretion to significantly change this. So we typically expect small spins for the black holes from isolated evolution. Okay, small. Except, so small for the primary. The exception is that maybe if we're in this type of case here, we have some stable mass transfer going on. If this orbit is very tight, we can get tides forming on this star. We can get this tidally locked, and this can spin us up and form a black hole secondary if we're in the right range of this being close enough that we can maybe get some tidal spin up. So we'd still expect the firstborn black hole to have low spins, but maybe the second one will have larger spins because of the tides of this black hole here. Now, if we were considering the chemically homogeneous evolution, things would be different here because we don't have the core envelope distinction, so we don't have the same worries on angular momentum transport, and we know that everything is rotating quite quickly. So chemically homogeneous evolution, we're going to have a slightly different stellar evolution because we don't have the core mix. So chemically homogeneous evolution theory is going to be similar but not quite the same. Going to have larger spins, could be around about 0.4 or so due to rotation. Okay. So it's similar, but not exactly the same. Okay. In terms of orientation, right, we expect these spins to be aligned with each other. They're rotating around in the orbital plane, so we expect these to be aligned. And it's a similar thing here, that we expect these stars to form together, be rotating the same way, or the mass transfer between them should typically spin them the same way. There may be some talks that could be applied here, but typically it's assumed that they rotate the same way. When we have the supernova kick, that can misalign the orbits. So if we get a kick that's out of the orbital plane, we could have two stars that were rotating the same way as they were orbiting around. But then one of them gets a kick that tilts the orbital plane to be something like that. So what were two spins that were aligned with each other then become misaligned when you change the orbital plane. So we expect some misalignment due to the supernova, could be some realignment due to mass transfer again, to torque the spins, but probably not too much as we don't have enough mass transfer to change spins significantly. So we, again, typically expect aligned plus, some kicks, misalignment in these cases. Okay. Often assume there's a big kick associated with chemically homogeneous evolution. Redshift evolution for these should follow the star formation rate. So we know that the amount of stars formed over time changes, so it will peak at different points. So this will then impact, obviously, the black holes formed from this. So it will be the star formation rate plus the delay time to go from stars to live their lives, evolve, and then form black holes, and then the timescale taken to inspire together. But it'll be set by this. Eccentricity is typically assumed to be small because there are various processes that circularize these stars throughout their lifetime as they exchange things. We go on now to the dynamical channels. Okay, dynamical channels. I should. Various types of what we call isolated evolution, but we know they're not exactly isolated. And these ones, which were called dynamical, even though we know they're not purely dynamical. The masses of these black holes get again going to be set by stellar theory. Going to set because they form by stars. However, we're going to have the dynamical effects that when you have an interaction, you potentially can get an exchange, and you preferentially retain the more massive black hole. So the binary masses might be more larger, because you preferentially select the most massive black holes to form the binaries. Additionally, this is something that was alluded to yesterday, we can also have hierarchical mergers in these environments. That potentially you have two black holes come together and merge, they inspiral together, form a new black hole. Now this new black hole will be formed and it will have a kick because of gravitational wave emission. Gravitational wave emission is not isotropic. You emit some gravitational waves in one direction and another more than other directions. So you end up with a bit of a kick, and that can be enough to then eject this from whatever cluster you're in. However, if you're in a small cluster, if you're in a big cluster and you don't get a particularly large kick, the size of the kick will depend on things like spins. It could be enough that you stay around inside the cluster and you go on to find a new partner and form a new binary that can match. And remembering that now you're a big black hole, you're more likely to find partners and form a binary. It's not unreasonable. And this is called a hierarchical merger because you have a hierarchy of first generation black holes formed from stars, and then second and higher generation black holes formed from previous mergers. So potentially our mass distribution could also be polluted by second generation black holes formed from previous mergers, third generation, fourth generation, and so on. Each generation should be more rare than the previous one, but potentially in very dense environments like nuclear star clusters, there could be a population of these guys. Okay, now what about our spins? Well, our spins, we typically expect them to be small for the same reason that they're just formed from stars, unless we're talking about second generation black holes. Second generation black holes are formed from mergers. The spin of the resulting black hole is dominated by the angular momentum of the initial black holes here. So the exact value you get depends on the mass ratio of the binary, but because there's lots of angular momentum here, for equal mass binaries, you can get spins of around about 0.7 or so for hierarchical. But as you make the mass ratio more extreme, the changes in the spin become less and less. But potentially you can have small spins from stars plus some higher spins from hierarchical mergers if they are present in that environment. This is In terms of orientation, this is isotropic again. Dynamical formation, just like for primordial black holes, will always be isotropic. The redshift evolution will again depend on star formation rate. However, the star formation rate in clusters is not the same as in the field. So globular clusters have an evolution over a different timescale. Nuclear star clusters, again, different. So star formation rate, I'll put a little prime there. It's not the same as star formation rate. So it is a different evolution. Eccentricity, again, this is dynamical, so there can be some eccentricity. Okay, so that's almost everything done. We have one channel left, so the active galactic nuclei, where we have things embedded in a disk. Here, okay, so potentially we start with black holes formed from stellar theory, but then we can have accretion from them being embedded in the disk, which can grow them further. The spins can potentially be grown from accretion. We have lots of accretion from the disk, so this can maybe get us up to larger values. And they will typically be aligned because we have the black holes embedded in the disk. The disk gives a preferred orientation. As material comes onto the black holes, it will spin them up, and that will typically spin them up in a way that aligns them with the orbit of each other. So we'll typically have a line. Redshift evolution will again follow star formation rate in an AGN environment, so that's going to be something slightly different again. And eccentricity should be small, as these should be efficiently circularized by being embedded in their viscous environment. So we have a whole host of different possibilities for what's going on. We have differences in masses. Some of these can be quite subtle, so the difference in different channels and how stars evolve. Some of them can be more noticeable, so adding in second generation black holes. We have a variation in predictions for how spins form. Some of these, although they're different channels, can end up being quite similar. So primordial black holes are predicted to have small spins because of the way that they're formed, and stars also predicted in some models if angular momentum transfer is efficient to have small spins. So different channels, but the same result of the prediction. These can be grown potentially by accretion. Second generation black holes can make things different. In stars, we might have the second born black hole being spun up by tides, perhaps. We're not sure exactly of the full details of this. But the orientation of the spins, isotropic for anything dynamically formed, aligned for AGN and isolated evolution, but not perfectly aligned. We know there are some processes like kicks that could misalign them, which is interesting. The redshift evolution is going to be different for each channel, and there's going to be some other redshift evolution which we'll get to that impact things as well. So there's some differences there. Eccentricity probably going to be small in most cases and difficult to measure, but seeing some could be a good sign of a dynamical formation. Yeah, star formation rate. This is me just saying that there's some star formation rate associated with each channel, but it's different. So star formation rate for the field is different from in clusters, and clusters is different than if you have a disk as well, and stars forming in a disk. So now, so you need to model the evolution of your supermassive black hole and the environment, and so it is a lot of physics that goes into those. Unfortunately, at the moment, we don't have a large redshift range over our detectors, so we don't see the full evolution of this currently yet. So I'm going to pay more attention to the masses and spins.
Christopher, one question. Two, actually. So when you say dynamical formation channel has some eccentricity, or actually for any of the eccentricities that you've quoted, this is eccentricity seen in band. Is that what you're referring to?
Yes, it is.
Okay, so seen, I mean, from the signal that we see in our ground-based detectors, that's what you're referring to, right?
Yeah, so I guess, I mean, for isolated, you typically expect it to be small, even if you see them further apart. If you were thinking about what if we say we're looking with LISA at a wider binary what we could see. And yet, I think you'd expect it to be small for AGN and isolated evolution regardless. I think it'd be more obvious in the dynamical channels. I think with the way that primordial black holes form, you have fewer close encounters. So I think the eccentricity would be most likely in a globular cluster or nuclear star cluster, something like that.
Okay, and about the AGNs, do we know, or is there an argument to say that whether the let's say the total orbital angular momentum of the binary will be aligned or misaligned with the, let's say, the accretion disk plane or something like that?
Yeah, so you normally expect them to be embedded in the disk, so they'd be co-rotating with it. So you'd normally expect it to be aligned there in the models. If you look at the potentially you could have things anti-aligned as well. That works out, but general misalignment should be sort of would be less likely. I think. I don't think anyone's done full 3-dimensional simulations of black holes embedded in disks there. So I'm not sure if there are some corrections to this theory waiting to be added when people take in the full 3-dimensional fluid prescription of the system. But typically, yeah, you'd expect them to be in the same plane as the disk.
Okay.
Okay, I have a couple of questions. Why the eccentricity is small for binaries formed in dynamical channels, even when in a dense environment? And that's because if we were just flip back to this channel here, that gravitational wave emission circularizes things quite efficiently. So eccentricity is going to be dampened down quite a bit. And that's the main reason why eccentricity is small when we observe it, because it will have been damped down by gravitational wave emission, unless you have something to excite it quite close to merging. A third body is particularly good for this, so if you have a triple configuration. Okay, and a question about which parameter among tilt and eccentricity will be more effective in inferring formation channel. Well, I will argue that it shouldn't be an or. You should always use all the information available, and it's only really by combining everything together that you get the full picture. And it's really these combinations which give you the full idea. So I want to move ahead now to take a look at some models here for different formation channels and the parameters they predict. So this is taken from a study I was involved with, so please bear in mind that I will be somewhat biased by this. And what we have here are plots. We'll just take a look at the top row to start with. And we have 4 different parameters plotted. The first is the chirp mass. This is a particular combination of the 2 masses that is measured from in spiral. So don't need to worry too much about the exact definition for our purposes. We just need to know, larger chirp mass equals larger mass overall is the main point. Q is the mass ratio. So coming back to the idea that different channels have different processes going on, different pairings, so that will map things differently. Chi effective is a combination of the 2 spins aligned with the orbital angular momentum. So if you have aligned spins, this will be positive. If you have spins which were anti-aligned with the angular momentum, those would be negative. If you have an isotropic distribution of spins, you'd expect some distribution centered on 0, because you are equally likely to have positive and negative spins cancelling each other out. If you have small spins, again, you'd expect it to be 0. So 0 is, you're not quite sure what it is, but it means you don't have large aligned spins, for example. And over here we have the redshift, so distribution of redshifts going on. Okay, and we have plotted here curves showing different channels. So CE, common envelope evolution, CHE, that's chemically homogeneous evolution, SMT, stable mass transfer. So those are the 3 what we would call isolated evolution channels. GC is globular clusters, so dynamical formation in globular clusters. NSC is nuclear star clusters, so dynamical formation in nuclear star clusters. We don't specifically have any models for in the AGN disk here, and we don't have any primordial black hole models. But just have a look at these. Hopefully we'll give you some idea of the types of variations that you can see. So bearing in mind that these all come from stars, we'd expect there to be a large overlap in the masses, and we see that this is the case. Most of the masses predicted are in a similar range. Chemically homogeneous evolution, you see, preferentially predicts larger chirp masses. That's because of the mixing results in a larger core, more mass being collapsed down, and also chemically homogeneous evolution only operates in a particular mass range in the first place, so it selects those regions. If you look at the masses of the nucleus star clusters, that's somewhat larger, as we can get the accretion going on and we get the dynamical pairing going on. Globular clusters, again, you can see there's some extra high mass systems. Potentially a few of these very high mass systems could be hierarchical mergers, and they have a slight preference over chemically homogeneous evolution to go to higher masses. Although when you compare it to stable mass transfers, it's really not that different. The differences between chemically homogeneous evolution and stable mass transfer is really set by the mass ratio. So the point at which the mass transfer rate becomes unstable. So you shouldn't, it's a little artificial to think of these independently. If they're really the same channel, it's just at some point the mass transfer becomes unstable. So there's some complementarity between these two distributions. You can see there's a difference in their mass ratio distribution when you look for the mass ratio distributions, which is, again, what you expect. It depends on the mass ratio of the stars to trigger between the two. Looking at the mergers here, the chemically homogeneous evolution has very close to unity mass ratios because that's the only point you can get chemically homogeneous evolution. You can have more unequal masses in dynamical formations and nuclear star clusters. You can get things growing and then finding a lighter component to merge with. Looking at chi-effective here, and this is where we need to start looking at the not just the top row but the rows below it. Chi-effective, first up in this row you see chemically homogeneous evolution predicts larger spins because that's spun up. Other channels are mostly centered around 0. For stable mass transfer, you can maybe see some larger spins from tidal distortions, but not too much. What we have going down here is the assumed birth spin of stellar black holes. So if you remember, we're not sure exactly how efficient angular momentum transfer is. So here we are basically saying, what if we varied assumptions about this so we could get black holes born with different spins? Okay, this doesn't really impact the chemically homogeneous evolution distribution because that's mostly spin up by tides anyway. But as you grow the stable mass transfer, and can't quite see it, but the common envelope is similar as well. As you increase these spins, you get larger positive chi-effective distributions because you have large, mostly aligned spins. Doesn't make much difference to where the peak is for the dynamical formation. It's always centered on 0 by symmetry, but you see it changes the width of the distribution. This is more potential variation in the range of values here. So the spins distribution does change. Looking at the redshift, this all sort of is governed by the evolution of star formation rate, which peaks at about a redshift of 2, and then you have a delay time, so then that gives the some trend here. Chemically homogeneous evolution varies slightly because of the stars that form it and the masses. We'll get to that a little bit later on. But you see that even though the physics of star formation in star clusters and globular clusters is quite different, it does kind of smear out and doesn't make too much difference at this rate. So it's hard to see the particular difference. So sort of to come back and summarize, there are differences between all of these. Some of these are quite subtle, some of them are harder to see. Because there's lots of overlap in the formation of these, it's very difficult to say for certain exactly what's going on. So it's really need to use all the information at your that you have available in order to try and determine what's going on and what type of sources we have. Okay, so as well as the parameter distributions, we also have the absolute number of detections. So different channels are predicted to produce black hole mergers, binary neutron star mergers at different rates. And so by measuring number as well as the distribution of masses and spins, that is also an important source of information. So what I have here is a plot of a number of predictions for the merger rate. This is binary neutron stars from a nice review article, which if you look up also has similar plots for the other channels. So binary black holes and neutron star black holes. Just to give you an idea of the variation. So the top few are sort of based on observations, so they're not theory-based observations. But lower down are for different channels. So isolated binary evolution, that'll be common envelope mostly, some stable mass transfer, triples, so dynamical effects with just a couple of, well, I guess 3 companions altogether. Globular clusters are less important than neutron stars than black holes, because neutron stars are less massive, so less likely to form binaries in these systems, similarly nuclear star clusters. The young/open star clusters are the dynamical formation I spoke about for what is normally assumed to be isolated evolution. So you can see there are many orders of magnitude of difference in rates. So that potentially would encode a lot of information. But of course, we need to bear in mind that what we see is the sum of these. So if something is a much lower rate than observed, it can still be contributing a small fraction to the observations. It's only if you're over predicting that you can say for certain that a model is wrong. So we're probably going to have a mix of these, and so we'll want to check, are the rates consistent with the, fitting the mass and spin and redshift distributions. Okay, so I think we're almost out of time. Yeah. But to try and finish up, this will be important coming back in a couple of lectures' time. We spoke a little bit about the fact that we have our masses of our black holes determined by stellar theory. Depends on how stars evolve. And what I want to end with just pointing out here is that it's not simple to say that this mass star gives this mass black hole. So we know that there's things like mass transfer and accretion that will change it, but even just considering a star in evolution, there's still some uncertainties. So here's a plot again from somewhat biased one of my study I was involved in, where we have a look at the 0 age main sequence, so the star mass just as it was turning on to become a main sequence star, compared with the mass of the remnant left behind, with 2 plots. The difference between these 2 plots is the assumed supernova explosion mechanism. 2 different mechanisms. This one here puts a gap in between neutron stars and black holes, whereas this one does not. We'll come back, I think, and talk about this in a future lecture about why this might be important, but we're not exactly sure of the way supernova explode during core collapse. So there are 2 different models here. So that's why there's a gap where we're not predicting anything in this mass range in this model, but we are in this one because of the way the supernova explodes. So if we ignore that now and then take a look at these other lines, these lines vary the different colors for different metallicities. So this is an astronomer's metal, meaning anything heavier than hydrogen or helium. So these different abundances of elements change the evolution because they affect the structure of the star and crucially the amount of mass loss. Remember, stars lose mass due to stellar winds. That's affected by their luminosity. This is very tightly linked to the metallicity. So the more metals you have, the more heavy elements you have, the more atomic transitions of lines you have in your material, the more lines you have, the easier it is for you to catch a photon. The higher opacity you have, the easier it is to lose mass due to winds because you can more easily catch the photons and get the radiation pressure. So the higher the metallicity, the stronger the stellar winds. So at a given starting mass, the lower the mass of the black hole you are left with at the end, because you lose more mass throughout your lifetime. This mass loss will also affect your orbital separation. As you lose mass, your orbit will tend to widen. and things like this. So this metallicity is very important. And this is why it's not just as simple as looking at the star formation rate to get the rate of black holes that you should assume, because you're going to preferentially form heavier systems earlier in the universe when the metallicity is lower. So it's star formation rate plus the delay time distribution and the efficiency of forming black holes, which varies with redshift. So that will also vary. Okay, so metallicity, very important for setting your mass distribution. And different metallicities give different range of black hole masses. Less impact in the neutron star range because that's lower masses. The winds are less important there. We have a mass gap also predicted up here, which I guess come back to again in a later lecture, due to a particular type of supernova, which I don't think you met last week. It was called pulsational pair, sorry, not pulsate one, called pair instability supernova. Pair instability supernova because when you have a very hot core of a star, at this point your star is supported by radiation pressure. However, when you get to very high temperatures, your radiation in the center of your star, your photons, can be high enough energy to convert into an electron-positron pair. Okay, get pair production. This is bad news if you're radiation supported, because your radiation suddenly disappears into electrons and positrons. So you're no longer radiation supported and you're going to collapse. As you collapse, you heat up and you get runaway nuclear explosions going on. And basically your entire star just blows itself apart. So there are no black holes predicted to be formed in this mass range because the stars are believed to completely disrupt themselves and leave nothing behind. If you're not quite massive enough to get into the pair instability, you can hit the pulsational pair instability, which is where you start to collapse, but you don't blow yourself completely apart. You just undergo a small explosion, blast off some outer layers, and this process will often repeat. You'll then be quite happy as a star for a small amount of time, then you start producing more electron-positron pairs, start collapse again, heat up, blast off more layers. And this means there's a range of stellar masses which all sort of result in black holes around about 30-something solar masses, because they go through these phases of losing mass until they're no longer in the pulsational pair instability range. So anyway, mass distribution of black holes, quite complicated. We don't predict things in the pulsational, in the pair instability gap. We have a pileup due to pulsational pair instability. Then we have sort of a relationship where we go down, we hit different amounts of mass loss, which result in different amounts of final mass. And we have a potential mass gap depending on supernova exposure as well. All of this depends on metallicity. So the and metallicity is linked to where you form in the universe. So this will evolve in redshift. So it's quite complicated. There's a lot of physics to understand. Mass loss rates are very important for things going on. So uncertainties in single stellar evolution will then impact the binary properties as well. So I think we'll close up for there now. And in the next lecture, we'll start moving on to talking about data analysis. So a slightly different topic, but we'll connect everything back at the end to how we go from combining observations, data analysis to constraining these theories at the end. So thanks everyone. I'll speak to you again later today, and we maybe have a couple of minutes now for some questions.
Yeah, so I had a question. So for the first thing is, what is the color bar here? Because I don't see anything. Oh, okay, this thing in the middle. Yeah, I don't know what that is.
Cool. Yes, I skipped over this because this is already quite complicated. So the scale bar meaning here. Yes, so this is referring to actually what's in the center here. So when we made this plot, we wanted to compare with observations. So each one of these lines represents a gravitational wave observation at the end, at the time. So this was back before the whole, it's around about the time that GWTC2 was published. It was after 1908-14 was published. I think it was after GWTC2, but anyways, it's not quite the most up-to-date, but these were the gravitational wave observations at the time, and this color bar here just gives the total mass of these binaries. So you can compare the total mass to the predictions for these formation here of these particular binaries. This is just a sort of an illustrative mass range. This is for single stellar evolution. It doesn't take into account all the mass transfer physics that goes on to complicate this. So it's just sort of as a ballpark to give you an idea of where things are ending up in terms of observations. And what we really wanted to point out was that, well, we have 1908-14, which has a mass in this mass gap range, which would lead you to prefer the delayed supernova model over the rapid supernova model.
Okay. Hello. I have a question from your slide 7, a couple of slides ago.
Okay. That's the wrong way. Come on, backwards. Here we are. Yes.
Yeah. So can you comment a bit on how these basically these probabilities for different parameters are plotted, and what are those? How certain are we of these things? Like how dependent they are on your simulation?
Yeah. So these are made from kernel density estimates of a bunch of realizations of simulations. The simulations themselves have a huge number of impact assumptions. So if you have a look at this paper, the appendices are basically given over to talking about these models. And yet there are a huge number of uncertainties involved in this. I think, as I started off saying in the first lecture, depending on your perspective, this is either good news or bad news. It's bad news if you want to take certain that these are predictions for what we should see. It's good news if you want to use the observations to constrain theories, because there's a lot to learn. So there's a large number of variables that can impact all of these models. And so there are some things which are quite robust. So for example, we know chemically homogeneous evolution can only happen if your mass ratio is close to 1. Okay, that's just by definition. However, we know that common envelope evolution and stable mass transfer, again, are separated by the mass ratio of the stars at that particular point when it becomes unstable. However, the exact point at which they become unstable is currently uncertain. The efficiency of common envelope in spiral, so the efficiency at which you can inject your envelope and convert your orbital angular momentum into orbital angular energy into energy to unbind the envelope, that's uncertain. So the separations you're left at the end is unknown. Details of the stellar winds, which are very important for determining your masses of black holes, very uncertain for high mass stars. So we don't know exactly what's going on with these. So that impacts your mass distribution and your delay times. Basically, everything you can think of about these systems is uncertain to some level. So whenever anyone tells you, this is their prediction, always need to bear in mind there's potentially some significant uncertainty on these.
Also, from slide 9, just a small clarification. You said that there are not supposed to be any remnant or black holes in the pair instability supernova mass gap. So, but that statement is only true for first gen black holes, right? Formed from stellar collapse. If we have hierarchical mergers, we can expect those mass ranges to be populated, right?
Correct. Yes. Excellent point here. So second generation black holes, we did speak about polluting the mass distribution. So yeah, second generation black holes would form in that gap. There are also other ways we can get black holes in the pair instability gap due to mergers, but due to mergers of stars rather than mergers of black holes as well. So the pair instability sets in because of the core mass. Right, we have a core, we have an envelope of a star. If the core gets too big, we're going to get pair production. Normally, the ratio of the core to the envelope is just set by stellar evolution. We know how that works, and so that sets the mass range. However, if we have another star come in and merge, we can potentially end up with a much bigger envelope for the same sized core. So maybe in something like a globular cluster or nuclear star cluster, we could have stars getting close together and merging, end up with a bigger envelope left behind, so that this can be below the Parameswaran mass gap. But when it collapses, if it swallows enough of the envelope, it could still grow in that mass range. So that's another way of getting in there. Equally, if we have accretion, so maybe in an AGN disk, have lots of accretion, we could start with a black hole that was formed by a star below the Parameswaran grab, and that grows it up. So there are a few ways around it. Hierarchical mergers, second generation black holes is one, stellar mergers another, accretion potentially a third, or if we are a primordial black hole, we weren't formed by stars in the first place, so there's no impact of the pair instability gap there.
Hello, so I have a question from slide number 7. So if you focus on this distribution for chi effective, and if you just look at the nuclear star cluster case, the distribution for chi effective is mostly centered around 0. But in the previous slides, you mentioned that chi effective should be something non-zero for due to the presence of second generation mergers, right? How do you explain that here?
Yeah, so good question. So chi effective is the weighted spin aligned with the orbital angular momentum. So if you have a second generation merger, that will increase your spin magnitude of your remnant black hole from 0 to something higher. However, it's still an isotropic orientation of spin. So it's just still equally likely to be aligned as anti-aligned. So that means when you're looking at the ensemble, it's still centered around 0. Another thing to note is that this is just dynamical nuclear star cluster. This is not the AGN channel. There's no disks added to these simulations. So we don't have the accretion growing things and aligning things in these simulations. That is missed out of these models here.
I see. So if we plot a like component spins, we should see some peak or a double peak in this distribution, right? Is that correct?
Yeah, so if we were looking at the component spins, chi1, chi2, they're often denoted as, yeah, then we'd see some different distributions going on there.
Okay, one minor clarification in this plot, what these black dashed lines correspond to here?
So the black lines just correspond to observations, and the dotted line here corresponds to a sum of the different channels.
I see. Thank you.